Okay.
Yep.
It's ready.
Yeah.
Oh.
Okay. Yeah, I think we can start. Okay, so hi everyone. So today we have Qingyu. I think everyone knows Dr. Zhu. He's currently an assistant professor of physics at UT Dallas. He earned his PhD in physics from University of Texas at Arlington in 2020, following a BS in geophysics from University of Science and Technology of China in 2015. He served as a postdoc fellow in UT Arlington and as ASP postdoc fellow in NCAR. His current research focus is on using data constraint modeling to investigate multi-scale storm time MIT coupling. So can you please take over?
Thanks everyone. So if you still have the memory, I actually came to Colombia the May last year. So when Judy asked me whether I can give another talk this year, I was a little bit hesitant at the beginning. So asked myself, am I that productive to do another program just within maybe 14 months? So, and then I realized it's exactly the 10 years since I first came here for a visit. So it's probably very unique, and it's probably meaningful to do another colloquium this year. So, and before sharing the stories 10 years ago, let's take what will happen this Friday. So this Friday, so that's the reason why I came here. So the sponsor, our ADSC office, I'm very fortunate to won the ADSC faculty fellowship. So which I will just lead a workshop focused on how to do the teaching practice. So this Friday is just the more or less the theoretical part. So first, I'll just give an introduction on what I learned from my students. And then our associate provost and the director of Center for Teaching and Learning and our UT Dallas, Dr. Karen Huxtable, will just present using active learning and in the classroom and laboratory, and then followed by the Q&A or just a simple panel discussion by me, Dr. Huxtable, and another visiting faculty, and I think it's as well. So we'll talk about more details this Friday. So we still have a session 2, which will occur maybe 2 weeks later. So that's the teaching practice session. All right. So this is what will happen this Friday. So then the question is, what happens 10 years ago? So 10 years ago, so I first came here, first floor to just participate the season summer school. I think this is either the last or the second to the last season summer school before it changed the name to the Boulder Summer School. So at the center, so it's the Mike, so who's supposed to be our head teachers at that time. And so I think many scientists here actually was guest lecturers for that summer school. So I was standing at the very left when I was a writing second year PhD student at UT Arlington. So Muro, who is a student of Mary, is also there, and many familiar faces in our field still were just my classmates. So this is what happened 10 years ago. And 10 years ago, I was also the first time I just communicated with Action and Art, try to run the 3D solver, dynamo solver. So the goal for me at that time is try to obtain the wind-driven electric field at low and middle latitudes. So NCAR 3D solver is a solver that calculates the global electric field driven by thermospheric winds and magnetospheric forcing. When I came back from the summer school, so what I did is just put the outputs from the 3-dynamo solver into GitHub. So, well, after adding the electric field, so the equatorial ionosphere and subsphere anomalies have been well reproduced. And so the blue line shows the thermosphere, the ETA, which also has 2 peaks further away from the EIA peaks. So which matches the statistics from the observation. On the right shows the non-hydrostatic effect that just due to a sudden introduction of the electric field at low and middle latitude. We saw some non-hydrostatic effect there due to just a sudden adding of the electric field at low and middle latitudes. And then I have been continuing working with Astrid and Art, try to complete the coupling between the beta and the 3D dynamo solver, as well as learn how to process the high latitude data. So here just shows an example that we did at that time. So we just bring the data from the swarm field current, and then use it to drive the beta together with the 3D dynamo solver. At that time, the field currents are identical in northern and southern hemispheres. And we actually reproduce the electric field, which is shown in the middle. So the middle one shows is the geographic coordinate, and the right one shows the statistics of the D2 measurements in the geomagnetic coordinates. So essentially, the morphology are the same. So the magnitude might be quite a little bit offset. There might be a little bit small offset between the magnitude. So this is what we did maybe 7 or 8 years ago. And then I became a SP postdoc here, working with Gang as an Astrid. At that time, so we are looking at how to just couple the ambient field current, use it to drive the GIDM. So this time we can just use a symmetric field currents in northern and southern hemispheres, and we just compare with the real measurements from the DMSP. So the blue or black color in the bottom shows the measurements, and the red color shows the results from the simulation. So as you can see, it shows very good comparisons between each other. So suggesting that the field current simulations can be used to drive the GCMs. So, and last year, so I also gave a clogging here. So I present some result we had for some moderate to intense storms. So the top panel shows the result from one of my previous undergraduate, who is now I think maybe some of you already seen her at Shine this year, a graduate student who are studying solar wind things. So the ambient field current shows that the electric potential patterns can be really different between the northern and southern hemispheres. Here, the BY problem be the most dominant factors just controlling these interhemispheric symmetries, while seasons may just do a plastic.
And can you tell me what the date is of that simulation?
So this date. So you mean this date?
Yes, the middle panel. What date? What
is the August 5th, 2011. So
yeah, okay, thank you.
Right. So 20 UT. Yeah.
Mm-hmm.
This is and this we also just compares the thermospheric density estimations just using different electric potential patterns. The bottom line shows observation, which shown in the red, in the black field current-driven simulations, which is shown in the red. The green line shows the simulation just using the empirical potential models. So as you can see, when we just drive the Gitton with the field currents, we can catch the very spiky structures in the observations. While when we use the empirical potential models, we just lose those spiky structures. So this is just again just demonstrate the one of the advantages using the field current to drive the GCMs. Then so we are looking at several moderate to intense storms. Then the question is, can we just step out of the comfort zone and just test our model capabilities during more extreme storms? And the storm we are looking at, we are a little bit ambitious, and we are looking at the 2024, the May storm in 2024, which is one of the biggest storms in the past 20 years. And unfortunately, we do have very good field current measurements during that period. So this is the IMF solar wind as well as the seen as the Supermax rain current index during this period. And as you can see that this storm is characterized by very strong IMF and both BZ and BY, and very high solar wind speed, roughly 700 kilometers per second, and just elevated to about 900 kilometers per second at the end of the storm. So, and the DST shows quite dramatic. The SMR indices shows very dramatic decrease at the immediately after 18 UT on day May 10th, and then show some recovery and then drop again, and the real recovery seems to start at around 2 to 3 UT on the next day. So this is the overview for the geophysical conditions for this storm. So, and we use a field current. We need to use the electron precipitation to just provide the conductance for high latitude. And what we use is called HD, the aurora spectrum and high latitude electric field variability. So, which is empirical model developed based on the DMSP measurements. So, so it can provide, we just do a statistic for every channel we have for the DMSP. So at the end, it can provide the differential energy flux in 90 energy channels on the different geophysical conditions. So comparing to the Maximilian spectrum, it just provides stronger component for the soft particles. So this is the aurora model we use. So, but this aurora model is the engine is developed just using the data from 2010 to 2015. No extreme storms occurred during that period. So the expansion of the aurora zone has not been tested during the extreme storms. So we just shows the total flux, electric energy flux, the comparisons between the default Ashley A and the SUSY measurements in the southern hemisphere. So as you can see, the Ashley, the aurora zone, aurora over Ashley is more forward comparing to the observations. Overplot, the blue and red lines are the field current from the anti field currents. So by default, actually aurora is also forward than the region 1, region 2 of the transition boundary of the region 1, region 2 currents. So on the right shows the DMS measurements during the last the biggest storm we had into the 21st century. As you can see, that the region 1, region 2 transition boundary seems aligned well with the whole aurora boundary of the aurora zone. So we need to just modify the expansion schemes in Ashley to just do a better alignment between the Field current and the electron precipitation. So what we did is go back to the DMSP measurements from the 4 superstorms we had in the solar cycle 23. So, and we found that the aurora zone can extend in terms of the core magnetic latitude as 38 degrees away from the pole. So we just modify the existing, we just modify some coefficient in the expansion scheme we have for the Ashley. And here just shows the comparisons of the aurora spectrum, the total energy flux just before and after the modifications, and its comparisons with the SUSY measurements. The blue lines here, blue dashed lines here shows the aurora flux distributions before we change the expansion. So again, it seems more poor than the observations. And then when we just modify our expansion scheme, we actually found a better alignment between the energy, the locations of those 2 peaks. Well, somewhat just indicate that we are just in the the right way to just change the expansion of the aurora. And then just here just shows the evolutions of the temporal evolutions of the cross-polar cap potential, as well as the hemispheric integrate Joule heating between 2 rocks. We just test 2 electric potential patterns. One is the electric potential patterns from the Field current driven simulation, and the other one is the Weimar electric potential pattern. Both simulations use the same aurora inputs, so the difference just indicate the differences in the electric potential. So on the bottom shows the distributions of the electric potential, which is pretty dim here, as well as the Joule heating and the certain at the May 10th, 22 UT. So as you can see that the top panels here shows the cross-polar cap potential seems comparable between 2 simulations, roughly around 200 kilowatt during the main phase of this storm. But the Joule heating in the Weimar simulations seems to be much higher than that in the Field current driven simulations. This is, as you can see on the bottom right, the Weimar driven simulation shows a very strong peak in the Joule heating on the dark side, while it's 300 something, while the maximum localized Joule heating in the Field current driven simulation is about 50 something.
That's a question.
Yeah.
So Joule heating, well, cross-polar cap potential is different than electric field, of course, but it's related. But is the conductance model the same in these simulations?
Right. The conductance is the same.
Identical.
Yeah, this is
how could the Joule heating be so different?
This is probably the aurora. So the aurora, well, the Weimar probably shows a smaller polar cap, but the electric field drops very quickly in the narrow, very fast in the short distance. So the E is bigger, but the distance is small. So the potential, which is the integral of the electric field and the distance, probably be comparable.
So the electric field in the field line current driven one there might be significant electric field in places where the conductance is not high. Is that?
Could be, yeah, but our simulation seems the aurora seems to have the well, and this comparable to the observations. So there could be some offset, but we actually saw something. The offset, if not very big enough, the potential pattern seems to be comparable. This is what we got from the solar. Yeah.
Okay. Well, onward.
Yeah, it's tricky part. Right. So what's the consequence? So then we just compare with the ion drift from the DMSP measurements. So the red line here shows the field line current driven simulation. The blue line shows the Weimer's the results from Weimer, and the black dot shows the observation. As you can see, those are from the northern hemisphere. So the dark side electric field from Weimer shows a very big overestimation, while the field line current driven simulations seems to have and it's more consistent with the observations, although there are some deficiencies, probably due to the offset of the aurora things. But all of the electric field seems to be reasonable from the field line current driven simulations. And
So
yeah,
so what's time? What's UT? This is during the main phase or early phase?
during the start of the main phase, we have
Start of the
we have actually compared all the tracks during the main phase and the recovery phase.
Yeah, because this drift looks like it's 800 meters per second or something like that. With the fuel line coming off. So it looks to me it's pretty low for major storms.
Right. Yeah. So so during this storm, so the drift is roughly 1,500 to 2,000 kilometers, but the polar cap expand a lot. So so the drift, if you can see that table, I just list comparisons during the main phase for all storms. So this seems to be the maximum drift I can see during this event.
Okay.
So on the right just shows the orbital average neutron mass density. So the blue line again shows the result from the Weimer-driven simulations. The red line shows the result from the field line current-driven simulation, and the black line shows the observations. As you can see, Weimer seems to have a very large overestimation comparing to the field line current-driven simulations, which is expectable because that as you can see that the Joule heating from the Weimer simulations shows overall it's overall greater than the field line current-driven simulations. So we can expect a larger overestimation from the Weimer-driven simulation.
So what happened after 6 UT looks like the red line opposed to Weimer rather than observation.
Right. I'll just touch that point later. So as you can see that, well, when being mentioned that the field line current-driven simulation still shows enhancement just around after the 6 UT. So what possible reason for that? So recently we just compare with the NO cooling from the Gideon and Sever. So here here we just shows several lines. The blue line shows the Sever. We just compare the height integrated the NO cooling flux. So the stable measurements and the Gideon. So as you can see, Gideon shows some very consistent, but just consistently underestimate those peaks. And then if we just do a orbital average, roughly 95-minute orbital average, so we can see that during the main phase, the Gideon consistently underestimate the NO cooling flux. So, and then I did a very naive experiment. if we just multiply the NO cooling by a factor of 50%, so here we show several things here. The blue line represents the variance. The orange line shows what we have in the previous line. It's just no change in the NO cooling flux. And then we just, you can see that after 4 UT, the average density continuously goes up until the recovery. But if we just naively just multiply NO cooling by a factor of 0.5, so we saw an earlier recovery for the neutral density, just around the recovery when the DST shows a consistent roughly 2 to 3 UT at that time. So during the main phase, we didn't see very significant change, but during the recovery phase, we see that's the time when we saw the maximum change. So I think that the underestimation of NO cooling, probably due to some coefficients, the errors in the coefficients in our GITM chemistry module probably play a role here. So this is the neutral density part, overall part. And also for this storm, it's also good for us to just examine some earlier series. So for example, the earlier simulations of the observations shows the neutral density, the high neutral density consistently have a low density cell on the dark side, which is just co-located with the convection cell. So but this knowledge is just established by data averaged over a very wide range of geophysical conditions, which, well, effectively represent the weak IMF and solar wind conditions. And also the simulation also uses a weak IMF and solar wind conditions. Then the question is, what does the downside neutral density looks like when we have a more extreme geophysical conditions? So for this storm, so at this UT, so the red lines, the BZ roughly around 0, while the BY is stable at around -40. So we can just take a look at what the downside neutral density looks like during this period. So our simulations shows some hotspots here, just located inside the downside convection cell, which actually can be measured by the observation. Here we just show the D-trend neutral density to show some spike structures. So this one looks great. This one seems okay. So this suggesting that the existence of this hotspot might be real. And we also compare the neutral wind measurements from the graphs. So seems also has a good consistency between the simulation and the observation. So so we saw a hotspot instead of a cell, a low density cell on the downside in this period. And then the question is why? Do we have very strong jaw heating below that hotspot? So, well, so here just shows the several comparisons of the neutral density. The first panel shows the neutral density and the jaw heating. Neutral density is in the color plot. The jaw heating is using the contour. So as you can see that all the hotspot is located pole of the region where the jaw heating is located. And this hotspot also accompanied by the very strong vertical wind, which is not located with the strong jaw heating there. So then where the jaw heating comes from. So we suggest that these very strong upward wind is just associated with the strong horizontal wind divergence, so which is shown on the bottom. So this vertical wind is essentially when the when we show the neutral wind is just show a very strong divergence. So the vertical wind comes up. And the reason why we can see this very strong horizontal divergence is because the ion drag is secondary during on the downside, because this is in the southern hemisphere. So the southern hemisphere is in the winter. So the ion drag is less effective than that in the summer hemisphere. So the pressure gradient force just play a more dominant role than the ion drag force. So this is what we have for the very extreme storm. So our summary comes here. So well, first, the field current driven simulations seems to be reliable during these storms. And we also see something, the downside neutral density shows a hotspot rather than the low density cell, which is probably due to the wind dynamics, the neutral dynamics in the high latitude. So that's essentially what we have for this storm. So, and then this is something that suggests that the field current simulations is good. Then we just bring a lot of, yes.
Question on the previous, yeah. So you said when for this very extreme storm, some adjustment to Ashley, right?
Right.
So after you make that adjustment, does the Ashley result be the same for the weaker storms? Does it affect?
Yes, nowadays we just use the update coefficient for other storms.
So it applies for most extreme storms.
Right.
Well,
Right. Yeah.
Earlier, weaker.
Right. Right. Yeah. So it doesn't change for the weaker storm. It's just only changed for the very extreme storm, which is not in our data set.
Okay.
So this is the this very extreme storm. Then we just focus on the another storm, which is the biggest one before the 2024 May storm. That is occurred in the 23-24 April in 2023. So this storm is characterized by a very strong dynamic pressure pulse occurs during the 3 UT to 310 UT measured by Discover on April 24. And this is actually caused very strong westward aurora electric jet roughly 40 minutes later. And this aurora electric jet actually induce very strong geomagnetic induced currents, roughly 50 ampere, which I think should be on the top, very close to the top candidates of in the past decade. So the GICs are important because it can just damage the transformers. And my perspective is a little bit different. Is that can this short night solar wind dynamic pressure pulse can significantly affect the ionosphere and thermosphere? It's only 5 minutes. Can it do a very strong impact on the IT system? If so, how? So again, we just use the field current driven simulation. And the first question is whether the field current captures this spike. So here we just shows the evolution of the field currents during that 10-minute period. So as you can see, there are some intensifications on the downside, where the both region 1 and region 2 exhibited a very strong enhancement around the 354 UT. So, again, we just use the field current driven, but this time the electron precipitation, well, because this spike, this spike cannot be seen in the IMF, the only on the only data set. So we just changed the way we just specify the electron precipitation. We derive the aurora precipitation from the supermag measurements. So here, that just shows how we do that. We did that. So here, first, we did a 2D Gaussian fitting for the horizontal measurements. Probably this actually has a this error, so we can just determine that the loss watt component of dV shows in this way. And then we just use the dV to calculate the ionospheric conductance using some old formulas. And then we just convert it to the total energy flux as well as this is the average energy. And so which will be merged by the Ashley. So and on the top on the right just shows the merge pattern. So and then we conducted 2 rounds. So round 1 is we just use 10-minute resolution field line current and aurora inputs. Round 2 is essentially the same, but we added in this 10-minute period, we added 2-minute input between the 350 to 4 UT during this period. So the case 2 can capture the information associated with the spike. Therefore, the difference between case 1 and case 2 just indicate the impact of the kinetic forcing change associated with this short-term solar wind dynamic pressure pulse. So on the top shows the field current inputs, and on the second panel shows the hemispheric power changes. So you can see that the hemisphere just changed the coordinate with respect to the field currents, roughly the same. So, and then on the third and fourth panel shows the differences in the cross-polar cap potential as well as the total Joule heating. So as you can see, there are certain, after adding the spike information, we do see a higher CP as well as a higher total electric, the Joule heating. So the difference is over 20% due to the dynamic pressure pulse in our simulation. So then we just want to get a snapshot. How do the kinetic forcings change due to this additional field line current and aurora precipitation information? So, and on the top shows the change in the ionospheric conductance. Here we just show the Peterson conductance. So the magenta dot shows the polar aurora zone from our case 2 where the spike is added. So as you can see that, equator of the polar aurora boundary, the ionospheric conductance increases, and polar of this PAB, the ionospheric conductance decreases. So indicating that the transition, so the aurora zone has a sharper gradient at its polar boundary. So this sharper transition or gradient will need a substantial enhancement together with the stronger field line current in the electric field on the downside. So as you can see, that the electric field that does not show very evident change on the downside. It shows some evident enhancement in the polar gap as well as on the downside. So, and the downside roughly 50% comparing with that in round 1. And then this enhancement in electric field together with the enhancement of Joule heating, the aurora precipitation leads a enhancement of Joule heating just equivalent of the polar aurora boundary from round 2. So, and the largest enhancement also occurs on the downside. And here, the electric field change should be the primary contributors as compared with the change in the conductance. So electric field changed more than 50%, while the conductance only show maybe 20%. So this is what we have in the high latitude. Then we want to see what happens at lower latitudes. So first, we found there's just by adding these the information associated with the solar wind the solar wind dynamic pressure pulse, we see this sudden enhancement in the upward equal speed drift and then going down, which suggests there's a penetration in electric field. It's at this time it's about 10 meters per second. And the penetration in electric field is known can lead to simultaneous global ionospheric density disturbance, SGDs. So which can also be seen in our simulated electric density as well as the DTC measurements. So we also see there's traveling ionospheric and ionosphere and atmospheric disturbances propagate away from the pole region, so which is also seen in the observations. So the phase speed is about 900 meters per second. And in terms of the magnitude, so currently our perturbation is about 1% in both electron and neutron density. But our auroral electric jet is significantly underestimated in GITA. So here, it's just output from the 3D dynamos solving. So what we have is 400 nanoterstar. The measurement is 5 times larger. So either we just we could underestimate the electric field very badly. So this is because the ambient field current cannot not be able to capture that fast varying mesoscale features. So now ambient field current needs a 10-minute window to just do the feeding, and its algorithm essentially provide the large scale features. So we could expect the more significant impact, maybe 5 times to 25 times, depend how much we underestimate the electric field. So, and we also want to see the vertical dynamics, which is the first project I did in my PhD. So the jaw heating, we just choose 5 different latitudes. This one is just exactly in the jaw heating zone. So we can see very large vertical wind induced in the aurora zone. The second panel is 10 degrees south, which is outside the jaw heating zone. So the vertical wind is much smaller, but you can still see more than 20 meters per second. So next to the aurora zone, just equator of the zones with very strong jaw heating. So, but this time the penetration in electric field plays a more important role. And the vertical wind becomes less and less evident at lower latitudes. And then you can see these structures, which probably is due to the divergence and convergence of the neutral wind due to the TADs. So by comparing these 4 figures together, so the one takeaway is that this solar wind dynamic pressure pulse actually can drive the thermosphere away from the hydrostatic equilibrium. But the strongest response occurs either in the aurora zone or just slightly equatorward of the aurora zone. The lower and middle latitudes may not be that off away from the hydrostatic equilibrium. So to sum up, so for this event, high latitude electrodynamics, we indeed see change in the ionospheric conductance, change in the electric field, and change in the jaw heating. And these changes need either penetration in electric field as well as the TADs which can be confirmed by the observational data mostly from the GNSS TTC. But there's a caveat. That is the westward aurora electric jet strength is significantly underestimated, and maybe we need a better forcing specifications in the future to better simulate these features. So overall, then let's go back to the section I probably read as a title. How far can we use these field currents in the simulations? So we actually did maybe simulations for around 10 very moderate to extreme storms. We found that essentially we found our DMSP comparisons, the measurements, the comparisons of the cross-track ion drift with DMSP are pretty good. So indicating that it could be a reliable electric potential patterns that used to drive the general circulation models. Even we just use electroprecipitation prescribed using an empirical model. So, and we also see that the field current driven simulations can significantly improve the storm time some sphere density estimations based on what we saw in the previous slide. Well, the difficulties or the challenges shows in how well the field current driven simulations can capture the transient features, those time scale smaller than 10 meters a minute, and mesoscale features 100 to 1,000 kilometers. So on the bottom just shows the conjugate measurements. Just show an example. If we are missing those mesoscale structures, how much uncertainties we could have. So here this is the 2023 March 13, 18 roughly. So we actually has a conjugate. This is probably the swarm satellite. This is a DMSP satellite in the southern hemisphere. So here we just shows the genome simulation compared with the DMSP measurements, and this is this mesoscale structures we can't capture it well. So therefore, we underestimate roughly 30% in terms of the neutral density. So this is something we are currently missing. But we still do not know what's the how much this error can propagate to globe. So I think with that, stop here and thank you for your time.
I have one. So my understanding is this storm was characterized by a very strong uplift of the ionosphere. Is that right? Yes. And so are you capturing any of that in your model?
Which
Well, I'm not expert on it.
The 24.
24. You mean the low and middle latitude ionosphere?
Well, there was very strong ionospheric uplift to the point, so
Yeah.
others here can describe it better than I can, but I just wanted to know if your model captured that.
Yeah, so I haven't taken a very detailed look at the ionospheric simulations. Currently,
Yes.
I only focus on the subspheric density.
Yes.
I can go back to take a
Yeah,
look
but
at
there are a couple. So
Yeah.
So you talk about this second storm that impulse in dynamic pressure, and you said that because the field aligned current is 10 minutes, so you won't be able to capture this mesoscale.
Right.
But what if in the Ashley model? Ashley is empirical, and so how often you are aurora precipitation is the aurora precipitation provide that mesoscale?
Aurora, so actually is not cannot provide mesoscale. It's just the large scale specifications. So
Right.
for this one, we actually use the Gaussian fitting for the just derive the aurora precipitation from the dB, which is also a large scale.
Also large scale, so
yeah.
it is not providing this mesoscale, and also the temporal, temporal.
Yeah.
What's the temporal?
So for this one is 1 minute. So supermag is 1 minute. So we update aurora 1 minute, but all the field current still 10 minutes. But
So
it's just a moving window with
yes.
yeah, right.
So temporal wise, the field aligned currents is 10 minutes and the aurora precipitation is 1 minute.
Right.
So aurora precipitation 1 minute is enough. But the scale, spatial scale
Yeah.
of aurora precipitation is not providing this mesoscale.
No, not this time.
So both should contribute to that probably.
Yeah, yeah,
Uh-huh.
right. Yes.
I was wondering for the three dynamo, do you go all the way to the pole or, and also, for the field line current driving? That's only limited to the high latitude.
Right. Yeah. So what? Yeah, we just use what Astrid did a couple of years ago. So just from maybe equator to pole. Yeah.
Equator to the pole.
Right.
So you don't need a dynamic boundary.
Well, yeah. I don't think we have a hard boundary here. Yeah. Right.
So very interesting for your dynamic pressure simulation. So you said you compare with GNSS, I may miss it. So how big is the perturbation in GNSS observed TECS compared to your observation?
Well,
I couldn't figure that out.
Well, it's difficult to just compare the DTC from the
Yeah.
This is 0.02 TCU. So we didn't actually
That's from
the observation.
GNSS.
Yeah, right.
Was your
So we didn't compare the so we didn't compare the DTC in
yeah, okay.
yeah, right. It's pretty small. So based on our simulation, I actually saw that it's pretty small.
Your observation.
In the Gitang simulation, currently our electron perturbation is 1%.
1% of
I think the DTC program also 1%. 1% with and without the 1% of the things without spike.
1% of total TC or compared with the observations.
One of the total TC from
One of total TC. So this one is observation you gave you 1.2 or something like that, or
0.02 U, so not the percentage. Yeah.
okay. But the TC, we know the TCs,
From
the TC units,
whatever. Yeah.
this is 2% or something like that.
Right.
Observation, yeah.
Right. Yeah.
Okay.
Yeah, so basically GATEM itself has enough resolution to simulate the mesoscale.
Right.
Yeah.
Yeah.
Mesoscale, even the process, the variability, and all that has enough set. This is the forcing that is not providing the mesoscale.
No,
Forcing,
yeah,
not
forcing,
enough,
yeah.
And I think the mesoscale forcing at high latitude, I think is often like mesoscale versus large scale. I sometimes is like almost like 50 similar comparable magnitude.
Right.
Yes.
That could be, yeah.
Yeah. I think it's often can be comparable. So therefore, because the forcing is not capturing the mesoscale, and then the process that dissipates that energy and high latitude energy and momentum will also be different.
Right.
Yeah. Yeah, like in terms of like TAD, TID, like PPEF, DDF, those are all different, in this when you're not capturing this mesoscale forcing.
Right.
Yeah.
Any other?
In your fitting, I think you fit the aurora and this is when you fit the aurora. Fit conductance aurora and you fit the field line current, use the field line current independently. What we usually see is this separate fitting will cause inconsistency when you put into a global electrodynamics solver,
Right.
and that generates, well, I would say artificial, but might not really represent the true electric field.
Right.
Global electric field in the system. So in this case, didn't you use the AMI to provide you a more coherent picture of both.
AMI is 5 minutes resolution.
You can do it in 2 minutes.
Yeah, but we don't have it.
Oh, okay. Well,
But AMI seems to use similar things.
yeah, AMI is
Yeah.
doing similar things. It derive the precipitation from both the imager and this ground magnetometer.
Yeah, I could ask Ganti whether that is AMI.
But you don't have or imagery in the storm, whatever. So you end up the same sense. So it's empirical explanation. There's a lot of uncertainty in that one. So it's,
So basically, the Ashley model, because you don't have the extreme storm, when you develop that. So basically, the result of that is that the Ashley model often gave an aurora boundary that is too towards the pole, and then like the maximum peak precipitation is too high, right?
Right. Yeah. So yeah.
That when you add it is
Right. So when we change the expansion, we assume the total hemispheric power won't change. So the peak density will decrease. The total hemispheric power we just compare with Gould, the Dunn and Paxton model. So seems comparable to the hemispheric power estimation. So we didn't change that extrapolation. Yeah, we just only changed the expansion. Yeah.
When you added the 4 storms from solar cycle 23 into Ashley, do you know how long of a period in terms of the storm that you did?
Yeah, so we just focus on DMSP measures the polar region roughly 100 meter a minute per cycle. So the storms we just choose maybe just covers the 2 days. If the storm lasts 2 days, we just choose all DMSP from that 2 days. Yeah, so 4 days we just choose that 4 days. Yeah.
I think we have a question from online attendees. Valerie, do you want to mute yourself?
Thank you. Thank you for a nice talk. Just my question about Gannon storm. You use vertical coordinate in kilometers. Did you erase the top lead for Gannon storm, or you still use the same top lead?
Okay.
The vertical top lead for the Gannon storm. Did you change specification of model, or you use standard top lead, something like 500 meters?
So we don't change any configurations for the model. We just change the forcing. Yeah.
Okay. So basically, we have in a pressure-based model, we have raised the top lead equivalent to 1,500, 700 kilometers for this storm. So I'm just asking, maybe you have some problems with specification of top boundary.
Yeah. That could be. Yeah, right. We are the top boundary of this storm in our Keaton simulation probably just 800. So about 800, we don't know anything about it. Yeah.
Okay, thank you.
Yeah, I think it's 3. So if you have anything you want to discuss with Qin, you can stay, and then let's thank our speaker again.